Hello everyone, I am Mazharul ANPA, a graduate student of Professor Dr. Madhav Nipane's Research Lab at University of Central Florida. Here in this talk, I am going to present one of my research project, which is a distorted Kagome metal NdTA 3Bi4. Basically, we studied the electronic band structure of this material. The technique we used is called angle resolved photoemission spectroscopy or ARPES, which is based on Einstein photoelectric effect. When we shine a sample with sufficient energy of photon, then electrons ejected from the surface of the sample, and those ejected electrons are captured by hemispherical electron analyzer. And using the momentum and energy conservation, we study the electronic band structure or plot this kind of graph like energy versus momentum and momentum versus momentum that actually determine the properties of the materials. So here, the energy of a photoelectron depends on also work function, which means the required energy to need an electron to eject an electron from the surface of the sample. So in order to dislodge an electron from the bulk of the sample, it has to overcome the binding energy as well. So here in this slide, I mostly talk about the structure of Kagome lattice and how we can study the electronic band structure of this kind of materials and what we expect from the RPS measurement. So the word Kagome is actually from the Japanese word, which is meaning that a hole in a basket. Here we see there is a hexagonal hole. It shares its six corners with six triangles. To study the band structure of this material, we can consider s-orbital tight binding model. The Hamiltonian is consists of the Hoping term and creation and annihilation operator and the Hermitian conjugates. If we solve this Hamiltonian, then we get two dispersive bands and one flat band. So that means along in the electronic band structure, here we see along gamma m k gamma direction, there is a direct cone at k and band of singularity at m point and a flat bond at e is equal to st. That means Kagome lattice host this kind of electronic band structure. So here I mostly will talk about the earlier work of Kagome materials or Kagome families. So FeSN is one of the AFM Kagome metal that actually hosts direct cone at around minus 0.42 eV, and there is a nearly flat band along gamma km direction. So another material is COSN that also hosts direct cone and flat bands. Another very interesting material is CO3SN2S2, which hosts actually the bile fermion in the ferromagnetic phase, but this bile loop actually disappears in the paramagnetic phase, and same thing also happened for the fermions, which is where we can see the fermions in the FM phase, but it actually disappears in the higher temperature above the TC in the paramagnetic phase. Another material is Fe3SN2, which material hosts the heavy or the massive direct cone. Here in the Fermi surface and constant energy contours measurement, we see that there is a small pocket and another triangular shaped pocket. And in the higher binding energy, we see that this pocket changes. That means they host the direct fermion in the electronic band structure at around like 70 MeV and around like 200 MeV. So these two direct cones actually located in different binding energy, but they are centered at K points. So another Kagome family is ReMn6SN6 and NB3S6 family. So TBMN6, one of the members of those Kagome family. So here it has the direct cone, which is located above the Fermi level, and this direct cone has the charge gap. And another Kagome materials is like HUMN6 and SN6 and ERMN6 SN6. They also host direct cone, and also we see that Fermi surface and constant energy contours has like hexagonal shape. So another Kagome family is NB3X8, which is a breathing Kagome. That means where we saw that in the previous slide that hexagonal shape shares six triangles, and if these six triangles are not equal in size, then we call them breathing Kagome. Uh, so NB3I8 is one of the member of the breathing Kagome family, which hosts multiple number of flat bands and nearly flat bands in the higher binding energies. So one of the promising cargo family is AV3SB5, which actually hosts a superconducting ground state and the CDW charge density wave, and also non-trivial band topology. So CSB3SB5, one of the member of this family that has superconducting ground state at around 2.5 Kelvin, and it also shows zero resistivity below this temperature. And it also has the CW phase, which transition temperature is 94 Kelvin. And we can clearly see that there is visibly Fermi surface reconstruction at gamma point and K point as well. So this circular pocket becomes double here, and the K points, the triangular shape K points, becomes also double and bigger in size in the CW phase. So in the electronic band structure along gamma k m gamma direction, we see that it hosts three band of singularities, where one band of singularity 1 is very close to the Fermi level, and it has higher order nature. So these are the earliest study of the Kagome materials. So our motivation was to find a new Kagome family that has band of singularity very close to the Fermi level, like 135, and also the flat bands also close to the Fermi level. And if it is distorted, then what would have the distortion impact in the electronic band structure? So we come up a family LNTHEBI4, which is uh, a distorted Kagome system. So one of the earliest member of this family is YBTI3BI4, which is a non-magnetic Kagome material, and it has two band of singularities and three flat bands. But this is a non-magnetic one. So our motivation was to grow a magnetic sample, which is NDTA3BI4. It's a soft ferromagnetic Kagome material. So this is the crystal structure of this material, where we see that the titanium Kagome structure, Kagome lattice is actually layered materials, which is divided by ND or bismuth zigzag layer. This is the top-down view of these materials, where we see that the titanium forms the hexagonal structure, and the bismuth intermediate layer also visible. So NDTH3BI4 is has a orthorhombic structure, and space group is FMMM, and number is 69. So this is the magnetization temperature dependent magnetization measurement, where we see that the transition temperature is 9 Kelvin, which is also revealed in the heat capacity measurement, where we see that the lambda like feature is present in the measurement, where this feature is absent for the non-magnetic LATA3PA4. So this is the 3D bulk brilliant zone and the 001 surface projected brilliant zone. So due to C2 distortion, this 6M and K point uh, splits into 4K prime and 4M prime, and 2K and 2M point. So this is the orbital projected fast mesial based DFT calculation, where we see that it has it hosts actually three band of singularities, which where band of singularity 1 is close to the Fermi line and it goes above the Fermi level, and another band of singularities are located around like minus 0.52 ev. So band of singularity at y and y prime, they are located in different energy, that actually the impact of the distortion. So it also hosts the direct cone at x point, which is also located slightly from the exponent. It depends actually for the distortion, and a number of bands actually crosses the Fermi level, which means that it has the metallic nature. And there are two flat bands, and there are also parabolic bands at around gamma point. So this is the to corroborate actually the DFT based fast specific calculation. We carried out the RPS measurement, where we see that in the Fermi surface is consist of three pockets. One is alpha, another one is beta, another one is delta. Alpha and another pocket at K prime point. So in the higher binding energy, in constant energy contours, we see that pocket at K prime increases with the higher binding energy, where the alpha, beta, and delta decreases in the higher binding energies. That means the pocket at K prime has the hole like nature, and alpha, beta, and delta has the electron like nature in the electronic band structure. So our calculated electronic structure Fermi surface fairly matches with our calculation. So then we studied the electronic band structure dispersion along the M gamma M direction, where we see that all three bands alpha, beta, and delta are present for both for all photon energy like 45, 50, and 55 VP, and it is also they are also present in the along the M gamma M direction, but only beta band is missing. This is bulk projected DFT calculation. That means alpha and delta bands are bulk, and on the other hand beta has the surface nature. So we also carried out the electronic dispersion measurement along the K gamma K direction in the both first and second billion zone. So these three cards actually been taken in the along the K gamma K direction in the first billion zone, and another also card taken in the second billion zone here. So where we see that at K point, and there is a Dirac cone exactly on the Fermi level, and there are two flat bands. So they are more clearly visible in the higher photon energy like 50 and 55 BB. So here we see the EDC, and we see there are two peaks, and these two peaks actually the contribution of these two flat bands. We also carried out the DFT calculation along the K gamma K direction and KZ result measurement, where we see that this electronic band structure actually support our measurement, RPS measurement. So here we take card along gamma M K prime gamma direction to resolve the band of singularities, and we see that there are three band of singularities at M point. One is very close to the Fermi level, and it goes up to the above the Fermi level, and the other two band of singularities around minus zero point 0.5 and minus 0.5 eV. So in the summary, we'd like to conclude that we studied the electronic band structure of this distorted Kagome system, and we find that it hosts three band of singularities, where band of singularity 1 is very close to the Fermi level, and it also hosts two flat bands and Dirac cone at K point. So these flat bands actually originated from the titanium 3dx and 3dx square minus I square orbital. So finally, I would like to acknowledge to my colleagues and the beamline scientist Shankwan Mu for helping to take the data in the beamline, and our theory collaborators and crystal growth and characterization Brandon R. Ortiz in the Oak Ridge National Labs. Thank you very much to listen to me.